Good morning, professors, faculty members, and my batchmates. I am Kriti Mawani, currently pursuing my bachelor's degree in aeronautical engineering. Today, with great honor, I will be delivering my seminar presentation on the topic black holes. So, let's start. This is the table of content. We will start our discussion with the introduction part, what exactly is a black hole, followed by its structure. Then we will see certain parameters associated with it like Chandrasekhar limit, Schwarzschild radius, time dilation, and gravitational redshift. We will then talk about the classification of black holes. Following that, we will see an impeccable phenomenon which is known as Hawking radiation. Then we will see the recent discoveries that allowed us to see the actual picture of a black hole, and then the Event Horizon Telescope which made all these discoveries possible. Lastly, we will see the conclusion part. So, let's see what a black hole is. Our understanding of black holes is based on the interaction between light and gravity. The gravitational attraction between huge objects is described by Einstein's theory of gravity, which associates the force of gravity with an analogous curvature of space. A black hole is a region of space where gravity becomes so strong that the curvature of space-time prevents light from escaping. To exist, stars must maintain a delicate equilibrium between their gas molecules, which produces a net outward pressure that is perfectly balanced by gravity's attraction, allowing the stars to retain their size over time. When a star shrinks to the point where its escape velocity equals that of light, the desired outward gas pressure becomes limitless. Because it is impossible to create infinite gas pressure, the star becomes unstable and collapses inwards. A black hole is what remains after a star is inadequate to overcome gravity and collapses inwards. There are different darkish items that astronomers make references to, however, they aren't black holes. For instances, there are darkish nebula which include clouds of cool molecules and dust that blocks out passing light. Now, we will see the structure of a black hole. A black hole has three parts. First is singularity. A black hole's entire mass is concentrated in an almost infinitely small and dense point called a singularity. Second is event horizon. The singularity is surrounded by the event horizon, the distance from the singularity at which its escape velocity exceeds the speed of light. A black hole does not have a surface, but it does have an event horizon, which is a particular boundary that surrounds it. The radius of an event horizon is a limit for light rays. Third part is ergosphere. It pulls the fabric of space-time along with it, an effect called frame dragging. This area, as you can see, is known as the ergosphere. Now, we will talk about a parameter which is known as Chandrasekhar limit. Chandrasekhar limit in astrophysics, maximum mass theoretically possible for a stable white dwarf. This limiting value was named for the Indian-born astrophysicist Subramaniam Chandrasekhar, who formulated in 1930. In the evolution of a star, a low or a medium mass star would first become a red giant, followed by a planetary nebula, and that it as a white dwarf. Chandrasekhar showed that it is impossible for a white dwarf star, which is supported solely by generated gas of electrons, to be stable if the mass is greater than 1.4 times the mass of Sun. If such a star does not completely exhaust his thermonuclear fuel, then this limiting mass may be slightly larger. For a high mass star, firstly, it would become a red supergiant. Then there would be a supernova explosion taking place, and eventually a star that ends its nuclear burning lifetime with a mass greater than the Chandrasekhar limit must become either a neutron star or a black hole. Now, let's see what a Schwarzschild radius is. The Schwarzschild radius is the radius defining the event horizon of a Schwarzschild black hole. It is a physical parameter in the Schwarzschild solution to Einstein field equations. A black hole is an object with a radius lower than its Schwarzschild radius. In case of a body with a constant mass density, the Schwarzschild's radius is proportional to its mass and thus to its volume. The supermassive black hole at the Milky Way galactic center has a Schwarzschild's radius of about 12 million kilometers. A black hole is an object with a radius lower than its Schwarzschild's radius. Schwarzschild's radius is linearly related to mass, and the enclosed volume corresponds to the third power of the radius. The average density of the volume enclosed in the event horizon of most massive black holes is lower than that of Earth's main sequence stars. The formula for Schwarzschild's radius is also given, which is equal to twice the gravitational constant multiplied by an object's mass divided by the square of speed of light. Now let's see time dilation. Time dilation is the difference in elapsed time as measured by two clocks in physics and relativity. It is either owing to a difference in relative velocity or a variation in gravitational potential between their point of origin. When used without qualifications, time dilation usually refers to the impact of velocity. The observer will measure the moving clock ticking slower than a clock that is at rest in the observer's own reference frame after adjusting for varying signal delays owing to changing distances between an observer and a moving clock, that is Doppler's effect. Time dilation explains why two working clocks will report different times after different accelerations. For example, time goes slower at the International Space Station, lagging approximately 0.01 seconds for every 12 Earth minutes passed. So, GPS satellites are adjusted accordingly to coordinate properly with systems on Earth. In frame of reference in which the clock is at rest, diagram on the left, the light pulse traces out a path of length 2L and the period of the clock is 2L divided by the speed of light. The total time for the light pulse to trace its path in the right diagram is given by delta t dash. Elimination of the variables d and L from this equation result in the final equation that you can see shows time dilation. Now let's see what gravitational redshift is. Because gravitational time delays the passage of time in extremely strong gravitational fields, it has an equal impact on time-dependent physical processes. That means that someone watching an astronaut in orbit around a black hole would notice that their clock was ticking slower, their hearts were beating slowly, and everything around them was slowing down. So, what happens when a beam of light is deep within the gravity well near a black hole? Gravitational redshift occurs in the light. When a moving object like a rocket ship is generating light, the light can be blue shifted or red shifted based on the ship's velocity towards or away from the viewer. If a ship were to accelerate away from you, the light from its engine would turn redder as it reached higher speeds. To depart a planet, a star, or a region around a black hole, light emitted from deep within a gravitational well must work against gravity. The photon must convert kinetic energy into gravitational potential energy as it travels from planet. We may expect that photons emitted from the surface of a star will appear redder to an observer far away from, if we remember that red photons have less energy than that of blue photons. This phenomenon is known as gravitational redshift. Although the gravitational redshift effect is minor, it has been measured in the light emitted by a white dwarf star and corresponds with general relativity predictions. Now we will see the classification of black holes. There are three main types of black holes classified by mass, which are stellar black holes, intermediate mass black holes, and supermassive black holes. We would see them in detail. First, we will see stellar mass black hole. A cluster of objects with masses ranging from 5 to 20 sun masses are known as stellar mass black holes. Stellar mass black holes are formed when big stars die violently. If the star is issue like our sun traveled through space as an isolated star, a black hole generated as a star of its demise would also be an isolated black hole. Because isolated black hole exist in space without a companion, they have little to eat. As a result, there is less material for them to gobble, allowing them to go undetected. Now, intermediate mass black holes. Intermediate mass black holes have masses that fall between the heaviest stellar mass and the lightest supermassive black holes, putting them in the middle of the astrophysical black hole mass scale. Intermediate mass black holes have a mass of more than 100 times that of our Sun. Because of the death of the star in our universe today, they are assumed to be too large to form. As you can see, there are just few solid candidates for the intermediate mass black hole class at the moment. Now, massive black holes. The biggest mass black holes are found at the centers of galaxies, are known as supermassive black holes. Galaxies are huge collection of stars that range in size from small galaxies with hundreds of millions of stars to largest galaxies with billions of stars. We expect the light from a galaxy to look like the light from a star since galaxies are made up of many stars. The ultraviolet, visible and infrared portions of the electromagnetic spectrum are where stars emit the majority of its light. All active galaxies have one thing in common. The supermassive black hole at its center consumes a lot of gas enough to power their energy production. The active galaxies provide food for their black holes, allowing them to develop. Now let's see what Hawking radiation is. Hawking radiation is the result of Stephen Hawking's prediction that black holes are not completely black but releases small amount of thermal radiation at a temperature. Due to quantum phenomenon at the event horizon, black holes emit Hawking radiation, which is black body radiation. Hawking radiation diminishes the black hole's mass and energy and thus also known as black hole evaporation. Because of the virtual particle-antiparticle pairings, this occurs. This happens when one of the particles fall in the other and the other escapes with the energy of a mass due to quantum fluctuations. As a result, black holes that lose more mass than they gain through other sources should shrink and eventually disappear. The Event Horizon Telescope. The Event Horizon Telescope project is a global cooperation that began in 2009 after years of theoretical and technical research. The Event Horizon Telescope is a network of radio telescopes spread around the globe. It observes the immediate surrounding of black hole event horizon, such as the one at the heart of Milky Way. The EHT project combines data from numerous very long baseline interferometric sites throughout the world into a single array with enough angular resolution to view objects the size of a supermassive black hole's event horizon. Now we will be seeing certain recent discoveries of black hole. First of them includes Sagittarius A star. Sagittarius A star is the constellation from which our center supermassive black hole derives its name. On May 12, 2022, astronomers using the Event Horizon Telescope released the first image of the accretion disk around the horizon of Sagittarius A star, produced using a worldwide network of radio observations. Sagittarius A star is the most researched supermassive black hole due to its close vicinity to Earth, and we are fortunate that it is not actively consumed. This provides us a great chance to see the area around it without being blinded by the accretion disk glare. The next candidate is Messier 87. The EHT collaboration revealed the first photograph of black hole near the center of galaxy Messier 87 on April 10, 2019. The image also revealed new information on its mass and diameter. The black hole's mass was estimated to be around 6.5 billion solar masses, and the diameter of its event horizon was estimated to be around 40 billion kilometers. To verify the results' dependability, 4 different teams took the picture. These methods include both CLEAN, a well-known image reconstruction algorithm in radio astronomy, and self-calibrating image processing algorithm for astronomy, such as the CHIRP algorithm. A regularized maximum livelihood RML method and the CLEAN algorithm were the final algorithm utilized. A fresh photograph of M87 black hole in polarized light was released in March 2021. This is the actual image of M87 star and Sagittarius A star taken by AHT telescope. The last candidate that we would talk about is Hermes 210. Rather than revolving stars, a black hole at the center of the dwarf galaxy, Hermes 210, is creating them. Recent discoveries reveal that a black hole in a dwarf galaxy is giving birth to a star. Black holes have been observed destroying stars over the years. However, rather than limiting star formation, the data shows that the outflow of ionized gas appears to be promoting the creation of stars. The black hole appears to be contributing the galaxy's current inferno of new star formation. Lastly, let's see the conclusion and future scope. The universe can be incredibly violent and severe environment. Only in the last half century have these frequently misunderstood items have been discovered and investigated. The depth and breadth of the known universe as well as the enormous success of relativity are shown by black holes. Sagittarius A star, our galaxy's own supermassive black hole, is visible for the first time thanks to data from Event Horizon Telescope. More observations are required to further constrain the models to monitor the variation of flow of matter in extreme conditions on different time scales and to image the black hole. Researchers currently believe that understanding the features of black hole is critical to furthering our understanding of the universe. This is the authorized certificate of the course that I've done on Coursera in order to understand black holes. This course has given me insight into the black hole physics. So I would strongly recommend this course to all those who want to advance their knowledge on the topic. These are the references. Any questions?
Yes, you use the parameter Chandrasekhar limit for white dwarf. What is the Chandrasekhar limit for a neutron star or a black hole?
Well, thank you for the question. The maximum Chandrasekhar limit for a neutron star is 3 times the mass of Sun. If this limit is exceeded, then star would eventually end as a black hole. Any more questions?
No.
Thank you so much for tuning in.